Alright, so in this video I'm gonna be explaining another important article with the title LG-GNN, Local Global Adaptive Graph Neural Network for modeling both homophily and heterophily. You know, most graphs are homophily. The labels of the neighbors are very close, they are the same as the original node. But heterophily, there are some data sets like Squirrel, Chamelson. Their state of the art is just 45%. Because not only they are related to their neighbors, but also the attributes of them are important. So this HK paper is very important, LG-GNN. Most graph neural networks are based on the homophily assumption, where nodes with the same labels or similar features tend to be connected to each other. However, real-world graphs often do not adhere to the homophily assumption. Currently, most researchers aggregate multi-hop neighbor information to discover more potentially relevant nodes. However, in the aggregation process of GNNs, the difference in modeling global and local information is not considered, inevitably leading to information loss. So motivated by this limitation, we propose LG-GNN, a local global adaptive graph neural network for modeling both homophily and heterophily. Specifically, we model the long-range structural similarity and local feature similarity between nodes from global and local perspectives in order to capture distant dependencies in highly heterophilic networks while reducing the mixing of locally dissimilar feature nodes, thereby increasing the effectiveness of information aggregation in highly heterophilic graphs. So this is an illustrative example of an academic graph with high structural similarity. So the question is how to model the local and global information within graph by making full use of topology and features. This is how we measure the homophily of a node, of course also homophily of an edge that you are familiar with. This is the structure of LG-GNN, which consists of two modules, including global information modeling and local information modeling. So how do you model this global information modeling here? Let's see. Nodes connected to each other often have different labels in heterophilic graphs, while nodes of the same labels are often very far with a long-range dependency relationship. The neighborhood differences of anchor node make it difficult for traditional GNN models to aggregate information from their neighbors, but long-range dependency relationship based on the anchor node is very meaningful for prediction tasks such as node classification. So we introduce a matrix S to capture long-range dependency information based on the global topology. It is believed that if two nodes have similar topology or neighborhoods, two nodes are similar. Therefore, given two nodes V sub I and this V sub j, the structural similarity between them can be iteratively calculated. As you see, we have S, then we find F. Again, we have F, we have S. So it's an iterative structure. And C is the attention. This C in the numerator is a attenuation factor, usually set to 0.6. So the higher this S is, the higher structural similarity. Now look at this, the higher S is, the higher structural similarity. Look, for every V sub I, V sub j, we look at the neighbors of them. Then we sum overall the neighbors of them. So we understand how similar are the two nodes V sub I and V sub j based on judgment on the neighbors of them. That's why the higher S, the higher structural similarity. In this way, we can calculate the structural similarity of nodes from an intuitive perspective. Considering that the structural similarity matrix S is defined for any node pair in the graph and is judged by calculating the global structural similarity information. Therefore, for the problem of how to discover potential relevant nodes of an anchor node in heterophilic graphs, the structural similarity matrix can be utilized to assign higher weights to potentially relevant nodes. So we take a look at the concept of random walk. We use P of Vi to represent probability from node V sub I to node V sub M. And Vi colon V sub M is just this one. This is a path of length M, consists of all nodes passing through the path from node V sub I to node V sub M. And due to random nature of walking process, the anchor nodes neighbors are visited with equal probability. For traditional GNN's aggregation, it can be considered as a local random walk with finite number of steps, while a random walk with two random nodes can be considered as a global calculation question. The probability, the higher the probability of walking between two nodes, the higher the similarity between the two nodes can be inferred. And given two nodes V sub I, V sub j, the probability of global random walk can be represented like this. So meanwhile, considering each layer of most GNN models is propagated and aggregated through one-hop neighbors of the anchor node, this process can be regarded as random walk. Therefore, the visit probability of each node can be viewed as node representation, and the combination of random walk and node representation learned by GNNs can be represented like this. This indicates that the L-layer GNNs can be simulated as random walk with length L, where the learned node representation contains information about the reachability of multiple nodes on the path. Furthermore, the node representation can be applied to GNNs to simulate a scenario of multi-layer stacking of GNNs. So we can obtain the representations of node V sub I and V sub j in an infinite number of layers. So infinite number of layers by substituting into equation 3 the structural similarity matrix now with global information can be calculated like this. Now, what about local information modeling? For a given anchor node V sub I, we need to construct a sorting list which sorts the intra-class nodes and inter-class nodes in the training set based on the cosine similarity. So intra-class node ranking list is defined as this. This is a ranking list. And Qi is less than Qi. Qi is the number of intra-class nodes in the same label as node V sub I. Analogously, the inter-class node ranking list is like this. So this is intra-class node ranking, this is inter-class node ranking. After obtaining the intra-class node ranking list and inter-class node ranking list of the anchor node, we combine them by splicing operation. And ranking of each node represents its true ranking. This represents the k most similar intra-class nodes and the k least similar inter-class nodes to the anchor node V sub I. Now, now we want to use this framework of adaptive graph convolution. The above two matrices collect more useful information for the anchor node from both global and local, allowing for the change of neighborhood propagation weights during propagation process. In other words, our goal is to increase the influence between intra-class nodes and reduce the influence between the inter-class nodes. This means that our global and local information matrices can assign different weights to the neighborhood of the anchor node and capture long-range dependencies on the long connections. So we can integrate homophily and heterophily. Formally, the feature propagation process in the alpha layer can be formulated like this. And then we just need to optimize the L of rank and your loss of GCN, for example. So we focus on semi-supervised node classification, and the loss function is mainly consists of two parts. This rank is the loss of learning to rank in local information modeling. And this one is the loss of adaptive graph convolution. So it integrates the global and local information into a unified model. They did experiments on Quora, Sightseer, PubMed, Texas, and all of these data sets, you can see the homophily of node and edges, the measure of that to see how difficult the problem is. And also it's interesting, we compare it with MLP as well. From 71, if we care about the neighbors, then we can come to 88 for Quora. From 66, if we care about neighbors, then we come to 77. But for PubMed, we don't see such a increase because maybe the neighbors are not important.